Hello students, in this video I'm going to be covering the section The Standard Normal Curve from the chapter The Normal Distribution. This will be part 1 since I'm going to show you how to find different probabilities or different areas under a curve using Desmos, GeoGebra, and Excel. The objectives for the following videos, the following series of videos are to use a probability density curve to describe a population, to use a normal curve to describe a normal population, find the areas under the standard normal curve, and find the z-scores corresponding to the areas under the normal curve. Let's start with defining what is a probability density curve. The curve used to describe the distribution of a continuous random variable is called the probability density curve of the random variable. Please remember our definitions covered so far. A random variable is a numerical outcome of a probability experiment. Then we have numerical outcomes classified as continuous and discrete. The discrete ones can be restricted to a list or can be listed, which is, for example, the whole numbers. And a continuous one cannot be restricted to a list and cannot be listed, which would be, for example, the numbers including the decimal numbers. If we think of it in a visual representation, think of the curve, the solid curve, describing the behavior of these two bar graphs or histograms to be the probability density curve. And those bar graphs or histograms could be also a visual representation of a distribution of a discrete random variable, because each bar represents a value that could be listed or could be restricted to a list. If we have a probability density curve, we can use that curve to find probabilities by finding the areas under the curve. If I want to find the probability of, let's suppose x is equal to a, for example, right here, it will be just this value right here. If I want only the probability of b, it will be just the probability of this event right here. If I want the probability for an interval values, I'll compute the area between those two values under the curve. Let's take this example right here. We know that our sum of probabilities for any probability experiment is 1. So the entire area under this curve is going to be 1. Let's take, for example, these two values, 7 and 8. And the area under this curve between these two values is 0.12. We have two ways of interpreting this area under the curve. This area represents the proportion of the population whose values are between A and B, or in this case 7 and 8, and the probability that a randomly selected individual will have a value between 7 and 8. Again, the entire area under the curve is 1. And the probability density curve represents the probability distribution of a continuous variable. Let's look at our first example using the same curve. What proportion of the population is between 7 and 8? Again, as per the information we can get from the probability density curve, the area between two values under the curve is the proportion of the population whose values are between those two values, and it's also the probability that a randomly selected individual will have a value between those two. If we're looking for the proportion of the population between 7 and 8, it's just the area under the curve between those two values. We have 12% of the population falling between 7 and 8, or if you want to write it in decimal form, 0.12. If a value is chosen at random from this population, what's the probability that it will be between 7 and 8? Again, the area under the curve between those two values could be also interpreted as the probability that if we select a value at random will fall between those two values, 7 and 8. So again, our probability is 12% chance, or 0.12 if you want to write it in decimal form. Using the same curve, let's try two more questions. What's the probability of the population that is not between 7, and 8. Now I want the rest. I want this portion or this area under the curve. I want whatever's after 8 and whatever's before 7. My only information provided is that the area between 7 and 8 is 0.12. If I know that the entire area under the curve is 1, what I can do is subtract from 1 the area between 7 and 8. 1 minus 0.12 is 88. So 88% of the population falls not between 7 and 8 or outside 7 and 8. You can also write it as 88%. If a random value is chosen at random from this population, what is the probability that it will not be between 7 and 8? That it will be smaller than 7 or greater than 8? Again, we had already computed it. I subtract from my total sum of probabilities the probability between 7 and 8. 1 minus 0.12 is 0.88 or 88%. You could write it either in either or forms, in decimal form or in percentage form. Both could be used to represent proportion and probability. Now I want you to practice. For example 2, I would like you to pause this video and try to answer these questions. What's the proportion of the population between 0 and 1? And what is the probability that a randomly selected value will be between 1 and 2? Consider that the area for the values between 0 and 1 is 0.63, and the area between the values 1 and 2 is 0.23. What is the proportion of the population between 0 and 1? The area under the curve could be interpreted as the proportion of the population. So just 0.63 or 63% of the population falls between 0 and 1. What's the probability that a randomly selected value will be between 1 and 2? We were given the area of values between 1 and 2 under the curve, which is 0.23. That's my probability of selecting at random a value between 1 and 2. 23%. 2 more questions for you to try. Pause this video here and then attempt the questions. What proportion of the population is between 0 and 2? Now I'm looking for the entire area from 0 to 2 under the curve. All we have to do is just add those 2 pieces of information that were given. 0.63 plus 0.23, and you can write it in decimal form or in percentage form. That will give me 86% or 0.86. What is the probability that a randomly selected value will be greater than 2? Now I want all of the area after 2 under the curve. We're not giving any information of these individual sections, but we do know that the entire area under the curve is 1. And I know that what I don't want, this portion right here, is 86%. What I can do is subtract 86 from 1, and it will give me the area that I'm missing for the complement of the area between 0 and 2. So the probability that a randomly selected value will be greater than 2 is 0.14 or 14%. Let's go over the normal distribution now. A population is represented by a normal curve, is said to be normally distributed or to have a normal distribution. In the previous 2 examples, we had this probability density curve, which we were not told if it was normal or not normal. We had these 2 probability density curves also before, but we were not told if it was normal or not normal. if you're being told that a probability density distribution is normal, then the following apply. The mode is equal to the population mean and also equal to the median. And if your normal curve is white and flat, we have a standard deviation, a population standard deviation that is large. And if the normal curve is tall and narrow, then we have a small population standard deviation. Here are a few examples of what we mean. Let's suppose we have two normal distributions, one that has a standard deviation 2 and another one that has a standard deviation 1. Both have the same mean. Both have mean 0. Notice how the curve that has a larger standard deviation is more spread out and more flat than the curve that has a standard deviation 1. The smaller your standard deviation is, the closer is your data clustered together, and the more narrow and tall your curve is. As we increase our standard deviation, our curve keeps getting flatter and flatter, and your data keeps on spreading out more. Now, if we have two curves having the same standard deviation but different means, they will have the same shape, they're going to be equally flat or narrow or short or tall, but they're going to be located in different sections on your graph. The center of your graph is going to be denoted by that mean. If I have mean 0, my curve is going to be symmetric at 0. If my mean is 5, my graph is going to be symmetric at 5 and it's going to be centered at 5. This applies when we have normal distributions. That's the information that we can take from the mean and the standard deviation. The mean tells me the center of my graph, where it is located, and the standard deviation tells me how spread out is my data, how wide and flat is my curve, or how tall and narrow. We have covered so far 2 of the probability density curve types. All of the normal distribution curves, let me show you a prettier slide. All of the normal distribution curves have the same behavior. They all have a bell shape because they're centered at the mean. They all are symmetric. And depending whether your standard deviation is large or small, you're going to have your data spread out apart or all clustered together. When we have only a probability density curve and we're not being told that it's normal, then it could be any shape. Could be right skewed, could be left skewed, could be evenly distributed, or bimodal, multimodal if you want to see it. All of the normal distribution curves, if you notice, are unimodal because they only have one lump. And later on today, we're going to learn about the standard normal distribution curve, which is a normal distribution curve, but it has its special feature is that the mean and the standard deviation are given. The mean for a standard normal curve is 1, and the standard deviation, the mean is 0, and the standard deviation is 1. That's what's special about our standard normal curve. The standard normal distribution curve has a mean 0 and a standard deviation 1. Any normal distribution curve can have any mean and any standard deviation, and a probability density curve can have any shape. In other words, the standard normal distribution is a normal distribution, but a normal distribution is also a probability density distribution or probability density curve. The properties of normal distributions: any mean, any standard deviation. All of the normal distributions have one mode. They're unimodal. That's because they only have one lump in the graph. All of the normal distributions are symmetric around the mode, which is the mean and the median, which takes us to our third property. The mean and the median of the normal distribution are both equal to the mode. The mean, median, and mode of a normal distribution are all the same. And the normal distribution follows the empirical rule. I hope you guys remember from previous videos what the empirical rule is, but if you don't remember, here's a slide to refresh your memory. The empirical rule says that within one standard deviation, we have 68% of the population. Within 2 standard deviations, we have 95% of the population. And within 3 standard deviations, we have almost all of the population, or 99.7% of the population. And we're going to be using this empirical rule to calculate areas under the curve. To compute areas under the standard normal curve, notice how we're talking about the standard normal curve, which is the one that has the mean and standard deviation given. The mean is 0 and the standard deviation is 1. The difference between the normal distribution and the standard normal distribution is that the normal distribution can have any mean and any positive standard deviation. The standard normal distribution has mean 0 and standard deviation 1. The probability density function for the standard normal distribution is called the standard normal curve. Please remember that we covered the z-scores when we learned about the empirical rule. The z-scores are points on the horizontal axis to the left and the right of the mode or mean or median, because it's the same under the standard normal curve. The mode itself is 0 or has z-score 0. Same does the mean, same does the median. And if we have values or z-scores to the left of your mean, they are going to be negative, and the values or z-scores to the right of your mean are going to be positive. When we're saying we're computing areas under the curve, think of what area falls between -1 and 1 z-scores. That is 68% of the population. What area under the curve falls between -2 and -1 z-score? That is 13.5%. What's the area under the standard normal curve? Sorry, I was missing the standard word. Under the standard normal curve is between 0 and 2. I will have to add 34 plus 13.5. So 47.5. And this is how we use the standard normal curve to compute areas between z-scores. I'm going to show you on the following videos how to find the areas under the standard normal curve using different methods, using GeoGebra calculator, using Desmos calculator, and using Excel and your TI-84.